Just keep disappearing.
Okay. So let us continue. So we sort of stopped in the middle of a theorem last time. We're going to complete the theorem. So this is like 2.3. I'm kind of mixing it with 1.4 and 1.5. So at some point I'm going to like assign 3 homeworks all at once, but a lot of them are very computational, so shouldn't be too much. So we're continuing here. Before finishing the theorem last time, I'm just going to tell you about some things that will make proving it a lot easier. These things are elementary matrices. This is an elementary matrix, what it is. It's basically a matrix you obtain from an identity matrix by performing a single row operation. So, for example, 1, 0, 0, 1. These are elementary matrices. Here I took I2 and I just multiplied the last row by -1. Here, so this is R2 times -1. I obtained this matrix by adding row 1 and row 2 in the I2 matrix. I obtained this one by taking row 3 plus 3 times row 2. Right? So I started out with an identity matrix, and I do a single row operation to obtain another matrix. I call these identity elementary matrices. Right? So we usually use uppercase letter E to represent an elementary matrix. Why are these so cool? You can actually use elementary matrices to do row operations. So, example, let E be an elementary matrix and A then EA is the matrix. It should be n by n. So in other words, I can do a row operation on A, and I can think of it as the product of A and an elementary matrix. So for example, suppose my E is that guy, 1, 1, 0, 1, which results from adding row 1 and row 2 in I2. Right? And suppose A is 1, 2, 3, 4. Then look at what EA gives us. EA would be 1, 1, 0, 1 times 1, 2, 3, 4. So the thing is, EA is going to be the matrix that results if I do the same row operation on A that I did on the E, right? Now what did I do with the E? I added the first 2 rows, which means EA should be the matrix that I get from this if I add the first 2 rows and put them in row 1. So let's actually see if that's true. How do I do this quickly?
1 times 1 plus 1 times 3.
Okay, so that's just 1 plus 3.
1 times 1 times plus 2 times 4, or no, 1 times 2 plus 1 times 4.
Right, so that's just 2 plus 4 over here. Right, 0 times 1 plus 1 times 3, so that's just 3. And then this would be 0 times 2 plus 1 times 4, so that's just 4. And so now I would get 4, 6, 3, 4. Now notice what happened here. The first row of A, how did it change? I added this row to that row to get that row, and I left the last one alone. That's exactly what I did with E, right? So I can actually describe a row operation as a multiplication by an elementary matrix. Now in practice, we'd never actually do this. You just do the row operation, right? But think of it in terms of elementary matrices. It makes it easier for us to prove things and talk about row operations in terms of multiplication, which a lot of times makes arguments easier. So we define this guy basically just to prove things. It's a tool we use to prove things. So now that we know what that is, it's an elementary matrix. The matrix you get from performing a single row operation on an identity matrix. And if you multiply that by another matrix, then the same row operations will be done on that matrix. That will be the result. So, a couple more facts on elementary matrices. Also note. Elementary matrices are always invertible. You can find the inverse by doing the opposite row operation. So for any elementary matrix E, there is a matrix E1 such that E1 times E actually gives us back the identity, right? So basically I obtained E by just doing something to an identity. All I have to do is do the opposite, which I can describe by another multiplication of elementary matrices, to get back to E. So if I got E by adding row 1 and row 2, I just make this guy the matrix that subtracts row 2 from row 1, and multiply by that, it would undo what I just did and give me back the identity, right? So anytime I do a single row operation, I can just undo it with another elementary matrix. And so every elementary matrix will be invertible. I can just undo the operation to get back to the identity. So that's pretty cool, and we're going to use that fact. another fact that we're going to use. I don't know if I should prove this. We sort of already talked about it. Then theorem A n by n is a matrix. Then the reduced row echelon form of A is either the identity matrix or has a row of zeros. I'll leave the proof to you guys. It's in the book. It's not a very complicated one. Basically, you just do the reducer echelon form of A, then you look at the last row. Either it's a row of zeros or it's not, right? If it has a row of zeros, you're done. If it's not a row of zeros, it means every row has a non-zero number. But if it's a square matrix, the only way for that to happen is there has to be a leading 1 in every row, which means there's a leading 1 in every column, right? And since the number of rows is the same as the number of columns, every column will have a leading 1, and so you'll have just a diagonal of leading 1s, right? So that should be clearly true. If you want to see the argument, it's like 2 sentences. It's actually in the book, but for now we'll just move on. Here's another theorem. This is actually quite an important one. The product of 2 invertible matrices is invertible. In fact, I can give you a direct formula for it. If A n by n, B n by n are invertible, then here's a formula for A times B inverse. Do you want to read ahead and know what this is?
B inverse A.
B inverse, A inverse. One of my old professors called this the shoes and socks law. So he's basically saying you can think of A and B as operations. So for example, if you put on your socks and then you put on your shoes, to undo that operation, you have to first take off your shoes before you take off the socks, right? So if you do A and then B, you have to undo that operation. You have to first undo the B and then the A. So he calls it the shoes and socks law. I don't know where he got that from. Right, so to actually undo a list of operations, you'd have to pretty much do the opposite in the reverse order, right? And that's what this inverse is telling us. The proof you can use direct computation. Assume A and B are invertible. Then, if you take this matrix and multiply by AB, if I take B inverse A inverse and I multiply that by AB, right? The associative law says I can multiply any pair at the same time. Right? A inverse times A gives me the identity. Identity times B will give me B. And so B inverse times B gives me again the identity. Right? So the inverse of this product is that, because when I multiply it on the left, I get the identity. And we have a theorem that says once multiplication on the left gives the identity, multiplication on the right would also give the identity. So this guy is the inverse. the end of the proof. We can prove a corollary, which your book uses, but I don't remember if it actually mentioned it. And I don't know if that's spelled correct. Any finite product of invertible matrices is invertible. So, i.e., if A1, A2, all the way up to AK are invertible, then I can actually give you a formula for what the inverse of their product is. And if I multiply them all together and I take the inverse, that will actually be, by the shoes and socks law, the product of everyone in the reverse order and their inverses. So the product of any two invertible matrices is invertible, and in fact any finite product of invertible matrices is also invertible, and that's how you actually invert them. So now, I was wondering if we could prove this. Probably can't. I'm not really devoting much time in this class to actually teaching you guys how to prove things, so I figure if you see me prove things every now and then, you can catch up on some things, along with the supplemental stuff that I gave you guys. So the proof here is by induction. Recall to prove a statement Pn that depends on n, which is normally taken to be a natural number, but it can be any non-negative integer as well. We must show 1, that P of 1 is true. This is called the base case. And 2, we need to prove that Pn is true. It implies Pn plus 1 is true. And assuming this is called the inductive step, so any basic proofs course would actually show you how to prove things like this. Induction is a very popular technique to use. It's sort of using the domino effect. So basically you have a list of statements that depend on n, and you prove that the first one is true by just directly checking it computationally, and then you prove that if some guy is true, then the next one is true, right? So if it's true for n, it will be true for the n plus first guy, right? So that gives you a domino effect. That way you know if it's true for the first guy, it's true for the second, if it's true for the second, it's true for the third, it's true for the third, it's true for the fourth, and you can literally knock everyone down doing it that way. So now I'm going to actually do induction on the k. So let me actually write down the statement. P of k is the statement A1 times A2 all the way times AK inverse is actually equal to this guy. That's my statement for any k. So I'm assuming they're all invertible, right? So in fact, the first guy's invertible. So if my k is 1 and I only have one matrix, then I know it has an inverse. If I only have one matrix, it's definitely true. It has an inverse because that's my assumption. If k equals 2, it is also true, since I know the inverse of two matrices is the inverse in the reverse order. I actually proved that here. This establishes the base case. So I proved that for the first two guys, it's clearly true. It's trivially true for if you only have one matrix. If you have two matrices, it's true by what I just proved over here. So I've just established the base case. It's true for the first couple cases. Now I want to prove that it's true in general. If it's true for any set of k matrices, then it must be true for any set of k plus 1 matrices. So now, assume pk is true for k matrices. That is A1, A2 times AK inverse is actually the inverse in the reverse order. Then what would happen if I have k plus 1 matrices and I want to find the inverse? Everything we can do. Right, so I know it's true for k people. I want to know it's true for k plus 1 people. How do you think of this?
So you just put a to the k plus, or a subscript k plus 1, then the inverse of that. And then multiply by the inverse of a to the k inverse.
You want to say the inverse of this times this inverse?
Times the rest of the inverse.
Yeah, that's what you call begging the question. That's what you have to prove.
You call the multiplication of a k plus 1 as bk, another matrix,
Yeah.
and there is an
Here, there's a product of matrices. Think of them as one big matrix, right? I can think of this as A1 to AK times AK plus 1, right? So this I can just think of as a matrix B. But now what do I have? I only have two matrices here to worry about. And I know the statement works for two matrices. So B times the AK plus 1 inverse is actually just AK plus 1 inverse times B inverse. But what is B inverse? It's just the inverse of a product of matrices, which I know what that is. This is just AK inverse, AK minus 1 inverse, all the way down to A1 inverse. True. Yes.
So if you're trying to prove something and you're using induction, you have to assume the variable belongs in a matrix.
Yes, it only works if you're counting integers. It works in the discrete case.
Is it only for these kind of problems or for any kind?
For anything. It works all over the place. Induction is like a super common proof technique. So anytime you have like discrete things that you can count them and you want to prove for any length list, induction is usually a nice way to go. So, very common proof technique. And this trick here is also quite common. A lot of times you can think of a bunch of things as one thing and then reduce a case of a whole long list to a list of two things. And then you'd have proved it for two things. And so it's inescapable. Yeah.
What if there are laws for theorems saying that you can only use natural numbers?
Come again?
What if you're like trying to prove a theory, but then if you only use natural numbers, you wouldn't be able to have like the 3 different cases of that theory?
You wouldn't use induction, you'd do something
But you
else.
would use induction.
Yeah. So. Induction is usually it's when you have this situation where you have a list of things, you want to prove something for a general list. I think we can actually go back to the theorem. So this is proof of theorem, I think 1.5.3. So that was the one that says if A is invertible, then the reducer echelon form is the identity. Then it will have a unique solution, AX equals B. Then A I can write as a product of elementary matrices, right? And those were all equivalent. So we proved up to B implies C, I think. Let's prove that C implies D. That is, if the reduced row echelon form of A is the identity, then A is the product of elementary matrices. If you're wondering why it's important that we know this fact here, I'm actually going to show you pretty much right very closely after this. Knowing this fact is going to help us to compute inverses in general. You know how we have a strategy for computing determinants? To figure out a strategy for computing inverses, I'm actually going to use this fact. So here, if the reduced row echelon form of A is the identity, then what does it mean if the reduced row echelon form is the identity?
It's a verb.
Hmm?
It's a verb.
No, I want to prove this. That's also true, but what does that mean? If I say the reduced row echelon form of A is IN, what does that mean?
A row has a leading ones for every row.
Sure, but when I say reduced row echelon form, what did I have to do to get there?
Row operations.
Row operations, right? It means that I can do a bunch of row operations on A to get to the identity. And remember how we can think of row operations, multiplication by elementary matrices. Then there is a sequence of row operations which I'm going to represent as elementary matrices. Right? So there are some list of row operations that I did on A to make it turn it into the identity. I.e., I multiplied it by EK to do one row operation, then I would have multiplied it by EK minus 1 to do another one, and I keep doing that. And after I complete all of them, the result is the identity. Right? So I did a bunch of row operations on A, which I can think of as multiplication by elementary matrices. The result is the identity. But I know each elementary matrix is invertible. And I also know the product of a bunch of invertible matrices is also invertible. I just proved that. So what I'm going to do is I'm going to multiply both sides by the inverse of this guy. What this means is this inverse here is going to kill that guy. I'm going to get the identity there. So I end up with In times A is equal to this guy, which means that my A, because the identity times A is just the A, and this times the identity is just that. And this inverse, I know what it is. It's actually EK inverse, EK minus 1 inverse, all the way down to E1 inverse. So A is a product of elementary matrices. In fact, it's the product of the elementary matrices that were the inverse of the guys that I used to turn A into the identity. That's actually a very nice fact there, because that's going to give me a way to figure out what the inverse of a random matrix is, of a random invertible matrix is. So that actually proves that C implies D. So once I know the reducer echelon form is the identity, I also know that A is the product of some elementary matrices. Now I'm going to want to show that my D actually loops around and gives me back A. If A is a product of elementary matrices, does it mean that A is invertible? Well, let's actually see if I can find the inverse given this fact. Assume A is equal to the product of these guys. Then if I multiply both sides by E1 E2, EK inverse, I would get E1, E2, EK inverse times E1 all the way up to EK. On this side, what would I get? The identity, right? Which is like the 1 in our matrix universe, right? So what did I actually show? I multiplied A by a matrix. The result is the identity. This means A is invertible, and its inverse is, in fact, this guy. Right? That will actually be A inverse, because it does what A inverse is supposed to do. I took it, I multiplied by A, the result is the identity. That's the definition of inverse. And so that actually proves our entire theorem. Which is a super important theorem, which we're going to expand a little bit by the time we end these 3 sections. We're going to expand on it just a little bit, but yeah, that's pretty important. Recall another pretty important theorem. A is invertible if and only if the determinant of A is non-zero. This is a super important thing. So, a little breather. Let's just take account of what we actually know. There's a concept of a matrix being invertible. What this means is I can take another matrix and multiply that guy by in order to get the identity, right? Invertible is sort of what we think of when we think of division in, say, the real numbers. For example, I can look at the inverse of 2. If it's because I multiply it by 2, I get 1, which is like the identity for the real numbers, right? So the idea is multiplying by the inverse of 2 is the same as division by 2. Division in matrices doesn't really work, but you want the same concept, right? So there's some matrix that when I multiply it by its inverse, I get the identity, right? So that's what an identity, that's what it means for a matrix to be invertible. Like such a number exists, right? In the real numbers, all numbers except 0 has an inverse, right? But every other number has an inverse in the real numbers. In the world of matrices, this is not true, right? First, you have to be a square matrix, and you have to have a non-zero determinant in order to have an inverse in the first place, right? So there's no general way to find an inverse and divide a matrix, right? So that's the first thing. That's another difference between the world of matrices and the world of numbers, right? So the idea is there are some matrices, the ones that are square with non-zero determinants, for which an inverse exists. This means there's a matrix that exists, I can multiply by that matrix to get the identity. Right? Now, once I know a matrix is invertible, I automatically know a bunch of other things. I know its reducer or echelon form is the identity matrix. I know if it's the coefficient matrix of a system, it has a unique solution. It will always have a solution, and it will always have only one solution. I know that it would be the product of elementary matrices, and I know that it's also invertible, and I know that the determinant is non-zero. Right? There are a bunch of things like, once I know any one of these facts, I know all the other ones. Right? So if you just tell me, oh, this is an invertible matrix, I automatically know if I reduce or echelon, it's the identity. I know that if it's a coefficient matrix, it has a solution. I know that its determinant is non-zero. And if you tell me, oh, the determinant is non-zero, I automatically know the inverse exists. I automatically know if it's the coefficient of a system, it has a unique solution. Any one of these things you tell me, I automatically know all the other things. Right? And that's a really powerful kind of thing to know. Right? So it gives you a lot of options. Just by knowing any one of these facts, you know all of these facts. It's a really nice thing when that happens in mathematics. It doesn't happen too often. When it does, it's really nice, and you take advantage of it like crazy. In fact, let me expand on that theorem now. So here's a theorem. The following are equivalent. A n by n is invertible. And we're going to talk a lot about what this means in general context, in different contexts as well, but for now we're just taking that by definition. It means there exists a matrix that I can multiply this guy by to get the identity. So if A is invertible, then I automatically know the reduced row echelon form of A is the identity matrix. I automatically know A x equals B is consistent for any B, which is an n by 1 matrix. D, I know that Ax equals B has a unique solution. There are a bunch of ways we can find the solution. We can use Cramer's rule, we can use the inverse, we can use Gaussian elimination, tons of ways, but I'll actually show you a couple more ways. I know that, in particular, they always list this one extra, so I'll just list it as well. This has only the trivial solution. I also know A is the product of elementary matrices. And I know that the determinant of A is non-zero. Did I get all the points? Invertible, trivial solution, reducer echelon forms identity, product of elementary matrices, consistent, da da da. Yeah. So those are 7 things about square matrices in which, if I know any one, I know all the other 6. Like any one, literally. If I start anywhere, if someone tells you this is true, all the other 6 is automatically true, right? Tell you that B is true, all the other 6 are right away true. Right? You don't even have to check them. And on the flip side, if you know any one is false, all of the others are automatically false, right? So if you know that the determinant of A is not 0, it means that the matrix is non-invertible. If you take the reducer echelon form, you will not get the identity. This might not be consistent. You could have infinitely many solutions, or you can have no solution at all. You'll automatically know that, yeah, that doesn't have a solution, that will be inconsistent. You can't write it as the product of elementary matrices. You will know all of that, just all at once. If I tell you one of them is false, they are all false. Tell you one of them is true, they're all true. So it's really neat stuff. Okay. Let's actually tell you some ways to find an inverse. We've been talking about what an inverse is. How do we actually find one? There are 2 ways. I'm wondering which one to tell you first, given the time that we have left. So I sort of want to wrap this section up, or these three sections up, by telling you how to find inverses and how we can use them. Let me tell you about two ways. Assume A n by n as an inverse. How do we find it? Here's one way. We know that in this case, A is the product of a bunch of elementary matrices. I know that this side is invertible, so I'm just going to take the inverse of both sides. And notice that this is this. I could have written it different in the first place, but that will obviously be true. In other words, I can figure out what the inverse of a matrix is by doing a bunch of row operations on the identity matrix, right? Which row operations? In fact, I sort of proved this earlier in the theorem. These are exactly the same row operations we use to turn A into the identity, right? If I perform those same operations in the other way, I would actually get the inverse of A. This means a good way to keep track of when I'm doing an operation on A and how it affects A inverse is just put them in an augmented matrix and do the row operations. So if I start with a matrix that looks like this, A augmented with the identity matrix, I'm going to find the reducer or echelon form of this system. Now if A is invertible and I take the reducer or echelon form, what's this side going to become? The identity. Right? Now I know the exact same operations on the identity is going to get me the inverse, so what's over here going to become? A inverse. So if I start with a matrix that looks like this and find its reducer or echelon form, the matrix that ends up over here is actually going to be the inverse of the guy that I started with over there. So let's actually do some examples. A equals 1, 2, 3, 4. Find its inverse. I'm going to tell you a bunch of ways to find the inverse, guys, and I'm even going to derive the formula that you got back in 1.4. I can derive it using this method, and I can derive it using the next method I'm going to show you. I'll probably use the next method. Okay, so the matrix 1, 2, 3, 4. How do we find the inverse? Make the augmented matrix. 1, 2, 3, 4 with in. Let's start finding the reducer echelon form. What's the first thing I'm going to do? Establish this pivot, which means I want to do what? I leave this alone first, right? Because I want that 1 there. I need to kill the 3. How do I do that? I can have row 2 minus 3 row 1. Okay. So that would be 3 minus 3, 0. 4 minus 6, minus 2. 0 minus 3, 1 minus 0. Now what I can do, I'm going to want to establish a pivot here. I'm not going to immediately divide through by 2 because that's going to give me a fraction. So let's start by killing the guy above there because I know eventually I can get this to be a 1. So what I'm going to do is I can just add row 1 and row 2, right? Row 1 plus row 2. 1 plus 0 is 1. This plus that is 0. This plus that is minus 2. This plus that is 1. And now I'm going to divide this guy by minus 2. So I'm going to get 0. 1. If I divide this by minus 2, what do I get? 3 over 2. Divide this by minus 2, what do I get? Minus 1 half. So, in fact, A inverse here is actually this matrix. Minus 2, 1, 3 over 2, minus a half. Is that true? How do I know if this is true? How do I know if that's actually the inverse?
Because you end up with the identity matrix.
Yeah, but what if I want to check? How do I know?
Oh, you put it 8 times.
Right, you multiply them. If I multiply them and I get the identity in any order, then it's actually the inverse. So let's actually check. If I take 1, 2, 3, 4, and I multiply by minus 2, 1, 3 over 2, minus a half, I would get 1 times this, minus 2, plus 2 times this, which is a 3, because the 2's cancel. I would get 1 times 1, plus 2 times minus a half. Over here I'd get 3 times minus 2, which is minus 6, plus 4 times this, which is actually plus 6. I would get 3 times 1, which is 3, plus 4 times minus a half, which is minus 2. 3 minus 2 is 1, 1 minus 1 is 0, 6 minus 6 is 0, 3 minus 2, 1. Checks out. Same idea. Let's do it for a slightly larger guy. I won't have time to teach you the other method, so we might as well just do another example of this one. 1 minus 2, 3. 2 minus 1, minus 1. Minus 3, 1. 4. A inverse equals what? What I'm going to do, augment this with the identity. 1 minus 2, 3, 2 minus 1 minus 1, minus 3, 1, 4, with 1, 0, 0, 0, 1, 0, 0, 0, 1. Start with our row operations. I leave this one alone. So it already has my pivot here, which means the next thing I want to do is what? Get zeros here and here. Right? So to get a 0 in this row, what do I do?
Minus 2 times row 1 plus row 2.
Right. Take row 2 minus 2 row 1. 2 minus 2, 0. Minus 1 will be plus 4, right? It'll give us a 3. Minus 1, minus 6. 0 minus 2, 1 minus 0, 0 minus 0. And to get a 0 here, I can simply take row 3 plus 3 row 1. This plus 3, 0. This plus minus 6. This plus 9. This plus 3. 0 plus 0. 1 plus 0. Here. Now what? I'm going to want to establish this pivot.
Let's divide that whole row by 3.
Wouldn't do that. Why wouldn't I do that? See, I'm going to get 7 over 3, 2 over 3, 1 over 3, which I'm going to be doing row operations with and adding fractions all that. Don't really want to do that. So I'm going to keep things in whole numbers and divide through at the very last possible moment. That's how I'm going to want to do things. So let's kill this guy down here. How would I do that?
Just add row 2 to row 3.
If I multiply row 2 by 5 and multiply this one by 3, I'd get the opposite numbers here. So I'm just going to do 2 operations at once and then subtract and add them. So for now, I'm going to leave the first row. 3.00. I'm going to take this one times 5. So it's 0, 15, minus 35, minus 10, 5, 0. This is row 2 times 5. Then I'm going to have 0. Multiply this by 3. Minus 15. 39. 9. This is row 3 times 3. So this one I'm just going to put that guy back. 3 minus 7 minus 2, 1, 0. Row 2 divided by 5. Now for here, I'm going to add the row 2 and row 3 from the previous section. 0 plus 0, 0. This plus this, 0. This plus this, 4. This plus that, minus 1. This plus that, 5. This plus that, 3. Now I can get a 1 here. I know I can get a 1 here by just dividing by 4. That's going to cause fractions here, so I'll hold off on that for a second. But now what I want to do is I want to turn this guy into a 0. Right? I'm still working on establishing the second pivot. And I'm going to do a very similar trick. Multiply row 1 by 3. Multiply this by 2. And then add them together. 3 minus 6, 9, 3, 0, 0. Row 1 times 3. The last row I'm not going to do anything. The second row I'm going to multiply by 2. And now I'm going to add those 2 to replace the second row. So if I add them, I would get 3 plus 0, 6 plus minus 6, 9 minus 14. What is that? 3 minus 4. Um, 0 plus 2 and 0. The last row stays the same. And then this row, I can move it back to So now what do I need to do? This is going to be, I can get a 1 by just dividing through by 3. This I can get a 1 by dividing through by 3. I need to figure out this one. I need those guys 0. So, oh, we're actually out of time. Finish this. Computation. Okay. So tell me your answer next time. Might even put this on a quiz, you never know. See if you guys actually try to finish it. So next time I'll tell you another way to find inverses, and we'll actually use the inverses to do some stuff with. And then I'll tell you about Kramer's rule, and that will actually finish the 3 sections, I think. I'll probably just give you the homework after that, which will be due Wednesday. No homework yet, no.